Abstract. This article investigates the continuity between Pyotr Kapitsa's philosophy of large energies and modern autonomous energy systems, including the hypothetical nuclear-powered missile Burevestnik, Stormbringer and compact fusion. It highlights how stability and control are embedded in physical laws, material properties, and field geometries rather than imposed externally. Key technical elements, such as high-temperature superconductors, high-entropy alloys, and high-frequency circuits, are examined as enablers of self-regulation. The paper also explores philosophical implications, including the transformation of human agency, technological sovereignty, and the emergence of energy itself as a quasi-autonomous subject. By integrating historical, engineering, and conceptual perspectives, the study situates contemporary nuclear technologies within a broader paradigm of energy autonomy. Stormbringer. A path to nuclear autonomy. In the history of science and engineering, few figures have managed to link abstract ideas with practical realizations of extreme energy systems. Pyotr Kapitsa was among these thinkers. His investigations of high electric and magnetic fields, his work with powerful generators, and his plasma experiments collectively formulated the philosophy of large energies. The concept that extreme energy flows can and should be governed not by human operators but by the internal structure of the process itself. In this sense, energy appears as an autonomous subject, capable of self-regulation when the physical conditions are properly established. The philosophical novelty of Kapitsa's approach lies in creating a fundamentally new configuration of rationality. In traditional engineering, management has always been an external function. Humans observe, correct, and direct processes. Kapitsa demonstrated that at extreme power scales, this approach becomes impractical. Physical processes are too fast and intense to be controlled mechanically or manually. Consequently, the engineering challenge transforms into designing physics itself so that it inherently ensures process stability. In Kapitsa's terms, energy must be managed by energy itself. High flows, fields, and resonances create conditions under which the system inevitably approaches a stable regime. This idea finds contemporary embodiment in unusual engineering precedents, one of which is the nuclear-powered cruise missile project known as Burevestnik, Stormbringer. The propulsion system of this vehicle, as inferred from open sources and expert analysis, represents a compact reactor capable of operating for extended periods without human intervention. The enigma of its operation lies precisely in how it can maintain controllability and stability within a confined volume, under vibrations, overloads, and high energy density. Traditional mechanical control systems are inapplicable. Control is realized through the reactor's construction, the properties of its fuel and materials, and likely through high-frequency and electromagnetic circuits that establish soft, self-regulating energy flows. In this way, the reactor operates according to Kapitsa's logic. It is not a human who holds the process, but the process itself maintains stability through pre-programmed physical laws and material properties. A fundamental characteristic of such systems is negative temperature reactivity, providing a primary self-regulation loop. As temperature increases, the reaction slows. As it decreases, the reaction accelerates. This effect establishes baseline stability and prevents dangerous overheating. However, for a compact rocket engine, this is insufficient. The volume is limited, neutron and thermal fluxes are extremely high, and the system's inertia is low. Therefore, Multi-layered self-regulation is required, including the geometry of the active zone, the spectral distribution of neutrons, thermal buffers, and materials with high temperature coefficients and radiation resistance. These physical circuits form a unified system in which deviations from the stable regime are immediately mitigated. The use of materials with high thermal conductivity and stability under extreme stresses is not merely an engineering requirement but an intrinsic component of the control logic. The properties of matter become a governing element, replacing external mechanical and electrical systems. Thus, the reactor's autonomy and its ability to operate over long durations without human oversight are ensured not by mechanics, but by the integration of physics and materials science. High-frequency electronics of large power also play a crucial role in such systems, yet they are subject to Kapitsa's logic. They do not replace physical laws but support them. Radio frequency fields and resonant circuits create soft energy flows, damp thermal pulsations, and stabilize energy transfer from the reactor to the working medium. The high-frequency system does not directly control the reaction. It establishes conditions under which the reactor and the working medium function safely and efficiently. This integration of physical and electronic mechanisms renders the system fully self-regulating and autonomous, demonstrating Kapitsa's principle that large energies govern themselves through their intrinsic properties. Comparison with contemporary thermonuclear projects further illuminates this philosophical and engineering logic. In next-generation compact fusion reactors, plasma control is entirely achieved through the properties of magnetic and electric fields, magnetic traps, high-frequency heaters, and resonant circuits replace mechanical adjustment, ensuring plasma stability. The compact reactor of Burevestnik is analogous in that it creates a self-regulating energy loop, where physical laws, constructive geometry, and materials form a unified control system. The difference lies in the type of reaction, fission versus fusion, and energy scales, yet the philosophical essence remains unchanged. Stability is embedded in the process itself rather than imposed externally. Understanding these systems requires considering several key elements of modern autonomous reactor design. First, the geometric configuration of the active zone and the placement of absorbers and moderators create conditions for natural self-regulation. Any local power increase instantly redistributes neutron flux and increases absorption, preventing exceedances of safe limits. Second, high-temperature materials with low thermal expansion coefficients and high radiation resistance preserve critical geometry throughout operation, while their thermal conductivity ensures uniform energy distribution and prevents. Third, the integration of high-frequency and electromagnetic circuits generates soft energy fields that smooth thermal flux pulsations, create stable temperature profiles, and stabilize the working medium's dynamic. Thus, construction, materials, and high-frequency systems are inseparably linked in a unified governing architecture, where humans act as architects of conditions rather than direct regulators. Modern high-temperature superconductors based on rare earth barium copper oxides, REBCO, enable the construction of coils with critical current densities on the order of 10 to the power of 5-10 to the power of 6 A per square centimeter under fields up to 23 T, allowing highly compact magnetic configurations in tokamaks. These coils are cooled with supercritical helium or hydrogen, providing thermal and magnetic stability, while integrated circuits damp pulsations and mitigate possible quench events. High-entropy alloys, HEA, and tungsten borides are used for shells and shields resistant to neutron flux, radiation damage, and thermal gradients, embedding protection and stabilization directly into the reactor. Thus, the engineering solutions of modern compact fusion reactors and hypothetical nuclear engines like Burevestnik share the Kapitsa principle of self-regulation. Stability and control are embedded in the system's physical fabric rather than imposed externally. The geometry of magnetic systems and resonant RF circuits allows for the confinement of plasma or working material in a stable state, creating resonant energy networks that adjust temperature and density profiles. Combined with cooling and damping systems, they form an integrated architecture in which the process stabilizes itself, while humans act as architects of the conditions. In Burevestnik, similarly, autonomy and reactor stability are ensured through a combination of physical geometry, fuel properties, and structural materials, possibly using high-frequency and electromagnetic circuits. From a philosophical perspective, these technologies illustrate a transformation in subjectivity and rationality. The traditional subject, who directly governs the process, disappears. It is replaced by the subjectivity of energy itself. The energy system becomes an autonomous agent with an embedded rationality based on physical laws, material properties, and field structure. Humans retain the role of architects and observers but lack direct control. This transformation opens new horizons for understanding technology, rationality, and power. Autonomous energy systems establish conditions under which the object self-stabilizes and functions. And the human subject ceases to be the center of control. Strategically and geopolitically, autonomous systems acquire special significance. Compact reactors and miniature fusion installations provide platforms for extended autonomous operation, independent of infrastructure or operators. This reshapes technological sovereignty. Energy autonomy becomes a condition of strategic independence. Simultaneously, such systems manifest a new form of power, not power over an object through external control, but power through the capacity to create conditions under which the object self-stabilizes and functions. Engineering and philosophy converge. Energy management becomes the management of conditions for the energy itself. Compact thermonuclear projects, ARC, SPARC, CFS, demonstrate Kapitsa's principle in practice. High-field REBCO magnets confine plasma, RF heating shapes and main. Considering Burevestnik as an analogous system in a different physical regime, one can infer that its reactor implements similar principles: autonomous self-regulation, integration of materials and field circuits, and minimal need for external intervention. Integrating these technical examples with Kapitsa's philosophical line reveals a new paradigm in engineering, where energy itself becomes the subject of action, and control shifts to the conditions and circuits of self-regulating physical processes. This principle opens avenues for philosophical and technical analysis of autonomous energy systems, their place in contemporary civilization, and their potential impact on strategic sovereignty and concepts of rationality in the 21st century. In conclusion, examining engines like Burevestnik and the prospects of miniature fusion reactors demonstrates that Kapitsa's philosophy of large energies, governed by physics rather than the operator, remains relevant. These technologies establish a new engineering rationality: autonomy, self-regulation, integration of materials and field circuits. Humans become architects of conditions, while energy itself emerges as an autonomous subject that stabilizes and regulates itself. Inaugurating a new chapter in the philosophy of technology and 21st-century engineering thought.